Okay.
There you go. You're good.
I'll be talking about smart city intersections and what I've been learning about real-time issues if we want to do something useful with them. So a bunch of people are involved, people from WinLab at Rutgers, Columbia University, and a number of students on many little and bigger things. So when you talk about Cosmos, they can, there can be various applications, but real time is sort of an interesting thing to consider. And the project that I'm interested in is specifically related to smart city traffic intersections, where I want to have low latency, I want to have very high bandwidth support, and I want to do edge computing, artificial intelligence type of stuff, all of the things that Cosmos offers. So Cosmos pilot site at Mount Building at Columbia is a perfect place for doing these experiments. I'm just presenting here a slide that summarizes anyway what the goals of Cosmos experimental testbed are. And it is exactly ultra high bandwidth, low latency, edge computing for novel applications, including something that looks like smart city intersections. One can reasonably make a statement that Manhattan or metropolises such as Manhattan have very complex traffic environments. And these days we hear a lot about autonomous cars. One statement that is true for environments like Manhattan is that individual autonomous cars will have a limited situational awareness in environments such as Manhattan. So if you take a look at that, at this picture here, the issue is that, well, the roads are complicated and any one vehicle really doesn't have access to all the data it needs if it relies only on sensors that are inside the vehicle. The other problem is that pedestrians are truly not obeying the rules, which is an issue that we keep learning all the time. So a view, if you're talking about a view from a camera or sensor from a car, that view needs to be somehow enhanced by sensors that are residing somewhere on the city infrastructure, or by getting data or doing the data exchange among the vehicles, at which point you start talking about not autonomous vehicles, but cloud-connected vehicles. So if you consider a smart city intersection, to be able to support cloud-connected vehicles, what you will need to have is low latency, high bandwidth wireless communications. You'll have to have edge cloud computing capabilities and machine intelligence to do automated processing. So indeed, the Cosmos node is a very good center of intelligence for a smart city intersection. You probably saw this photograph earlier today, but this is Manhattan sideways, and this is the location of engineering building, mud engineering building at Columbia University. This is Broadway and this is Amsterdam Avenue. So this is the pilot site. And this pilot site is once again right here. And what we have installed at that pilot site is, first it is Amsterdam and 120th Street, and we have radios, cameras, edge computing nodes with GPUs and FPGAs. And for this particular presentation, I'm talking about experiences based on cameras that are installed on the 12th floor, fairly high up. So the use case that I'm talking about is about interaction with cloud-connected vehicles in the sense of Cosmos. So what we sort of set up a use case. We say we'd like to collect data using sensors from vehicles and very particularly cameras to identify all vehicles and pedestrians, and based on that input compose the radar map of those objects, where the objects are vehicles and pedestrians. And after composing that radar map, broadcast that map to all participants in the intersection, very same vehicles and pedestrians, in real time. So that's sort of a use case that I'm talking about. And this is going to be an illustration of I'm going to show you a short movie here but I would like you to pay attention to the fact that in the lower corner, you will see the actual video, and the rest of the area presents the blue or red vectors, velocity vectors. Blue are vehicles, red are pedestrians. And these are videos captured from the 12th floor of Columbia Mud Building. So let's see, this is gonna run quickly enough. Yeah, it's running. So you can observe that it is possible. You see these red dots or vectors. They're actually pedestrians that are very, very hard to see in the real video. But if you do spend some time manipulating and modifying the algorithms, it's possible to capture them. So the idea is indeed that we capture such a video and attempt in real time to come up with all of these vectors and broadcast and create this map and broadcast this map to everybody who participates in the intersection. So that's what we're considering. Let me go back to the presentation mode here. So it's not a simple thing actually. Why? Because you're dealing with cameras, you have latencies in video encoding, in communications, in streaming and video decoding. To be able to create a radar map, such as I described, you need to have deep learning based object detection and tracking. And finally, you need to close the loop to communicate that radar map, to transmit that radar map back to all the participants. And you want to do that in real time. So it is actually a fairly complex thing. So what is real time? Well, I'm going to define my own real time based on what I think may be reasonable target. So for something to be useful, to get some useful input, I apologize, there is something on my screen that you may be seeing or may not be seeing, probably not. Everything has to happen fast enough to support the traffic management or so that vehicles can do something useful fast enough. So consider a vehicle that is moving at 10 kilometers per hour, which is 6 miles per hour, or about 3 meters per second. So what happens if you move at 3 meters per second? Well, I would like to divide this number by 30 because videos are very often captured at 30 frames per second. So if I divide 3 meters by 30, I'm going to get 10 centimeters. And that tells me that in one frame, the movement of that vehicle is that much, 0.1 meter. If I'm capable of providing feedback, close the loop within this amount of time, the vehicle moved just for 10 centimeters, that may be reasonable in terms of preventing an accident or something. You may choose your own numbers, but let's say that that's a target. Arguably, this is useful to potentially prevent accidents. Essentially, what we are asking for or setting as a target is round-trip latency of about 33.3 milliseconds. So what contributes to the time consumption when you're doing the processing? First, we're focusing on inference. So because these models or these methodologies are essentially based on machine learning techniques, you need to train the system and so on. So I'm not talking about training here, I'm talking about inference. I'd like to close the loop in 33.3 milliseconds. So a camera or a sensor is one part that contributes to the latency. Sensing, the actual physical sensing, video encoding, streaming, then communications through the wireless infrastructure, the edge internet infrastructure, through switching equipment and over different protocols. And finally, the actual processing of object detection and tracking in edge computing servers. Finally, completing the closed loop. So those are how do you break down where does the time budget get eaten. The fact is that the simple thing to do, or the most obvious thing to do, is to use high quality surveillance camera, which are IP based and definitely use video compression. So what kind of constraint or what kind of issues does it create from the perspective of real time? So if you break down latencies, if you look at pure image sensors, CMOS image sensors for pixel value acquisition, and if you look at very high quality, very high resolution image sensors, such as this particular one by Sony, very high resolution, it can work at very high frame rates. You know, it is something that contributes about 10 milliseconds of latency. So lower resolutions that may be good enough for our needs will have even better resolution. So that is the contribution of the actual sensors. The next thing is video coding and decoding for compression. The compression algorithms, video encoding, are truly impressive, but they can impose arbitrary delays because of the fact that they have temporal encoding of different types of frames to facilitate good compression, because of the fact that vendors who build these cameras construct their own buffers that may not be obviously described to a user. And because of the fact that all of these cameras can be specified by user to be in a particular mode of operation. So it is very common to see latencies of 1 second and more because of these issues. There is more. The higher level protocols or engines for processing these data, again, are a function of how did you set up the tool. And because of the setup of these tools, you can have multiple second latencies. So our goal was 33.3 milliseconds. Now we're talking about some number of seconds. So that's how the cameras contribute to it. So this is like sort of an attempt to illustrate that if you were to be taking a video and trying to see the local time and compare what is the latency because of these factors, you see this number 51 and 50 here, where these are the seconds. So it's easy to see seconds and more. So the next thing that we're talking about here, and this thing is right in front, something is obscuring my screen. So for a few seconds, I'm going to move this aside. It's going to be a little bit smaller. Hopefully you still see. So the illustration that I have here is I have a camera, I have an internet link, I have a wireless part of the communication. Then I have a server, computing server here. In the upper diagram here, I have a GPU board. So this GPU board is co-located with the camera. Or I may have a setup where my GPU board, graphics processing units, is co-located with the server. So there is this issue: what is the right thing to do, or when is what a right thing to do, and what would be the implication on the latency? So I'm going to go back to the full screen mode. Very quickly go through this. We do have in our possession, and there is stalling all of these different components. Some of them already exist, but you can get and buy equipment that we've heard about from other presenters as well. Things such as NVIDIA Jackson's rather powerful GPU engines that can be physically co-located close to the cameras, whose power consumption is some number of tens of watts, or you can have truly powerful GPUs such as Ampere A100 next to the servers. So it is not clear always that you will be able to do sufficiently good and sufficiently accurate object detection and tracking by these truly edge devices. Sometimes you need to pass the data all the way to the server and process the data in the server. Or you may purposely just want to do that as long as you have super fast optical or other link that will easily support whatever the communication bandwidths are. Because of the, frankly speaking, privacy considerations and issues with IRB at Columbia University, I've chosen to work with 12 floor cameras. one thing that is problematic is that if you take just off-the-shelf models or deep learning models, you will have significant issues with very small pedestrians. So a good amount of work with my group went into customizing solutions and increasing the performance for accuracy for small pedestrians. I'm not going to run this video. This functions pretty well. These experiments were run at the Cosmos pilot site. We've collected more than 10,000, many more than 10,000 frames. Those of you who work in this area would appreciate the fact that to do deep learning, you have to have annotated data. So many hours of work went into annotating the ground truth and training these models such that we would be able to actually detect very small objects. Somebody earlier in the presentations mentioned background subtraction, yet another method that is suitable for this type of application. So here I'm illustrating just an example of a couple of results that refer to the sort of make a statement about as a function of the resolution of a video, 1080p, which is HD or slower or smaller resolution. This particular A32 resolution, it's just a number that's conveniently used for one particular YOLO model for object detection. One has to note that the results always indicate that you're talking about some amount of accuracy. The accuracy in detection vehicles which are larger, it is notably higher than the accuracy of pedestrians. So this is a continuous issue and still an issue that has to be worked on and improved, the accuracy of detecting the pedestrians from these 12th floor videos. So a couple of words about the speed. So these are the actual speeds that we have measured with our data sets, with our videos that we have acquired. So an important component in this story is that you have to have a algorithmic flow that is highly optimized. So if you just work with deep learning frameworks such as PyTorch or TensorFlow, they're really not built for real time. Well, NVIDIA did create flows which support optimized operations, meaning they minimize the number of buffer copying and so on, and this thing is called NVIDIA DeepStream. And we implemented various things in NVIDIA DeepStream. So this indicates here that we can run 832 by 832 resolution at about 40 frames per second, which means that we're better than 30 frames per second. So that is, however, strictly for purposes of object detection and tracking. And then we can run faster for a little bit lower resolution. What this doesn't have, and then even faster for lower resolution. Now, what I don't have numbers yet for is latencies that are eaten by communications delays from cameras to the server, to the Cosmos server, not to the edge. It's not the NVIDIA Jetson solution, but the one that the Cosmos server works with. So it is reasonable to expect that when we push this through, we will be able to, we're hoping that we'll be able to reach for these types of resolutions, will come close to 30 frames per second, which would be real time. Now, a little bit of a reminder here. If you have HD quality video, that's 1920 by 1080 pixels, 24 bits per pixel. Well, the number of bits, the number of bits per second that I have to transmit at 30 frames per second is 1.4 gigabits per second, essentially. That is for raw video. The compression is truly powerful. So they, on average, if you do compression for HD, you communicate about 12 megabits per second. So that's a testament to the high quality or achievement of our colleagues who do video encoding. Now, however, I told you about all of these latencies that are somewhat unpredictable when you use video encoding. So who knows? Maybe one will want to consider in the future either using this type of video coding, or saying that the amount of wireless bandwidth as well as the bandwidth through the optical channel are such that, oh, maybe I can send even raw videos and not have to deal with the delays the video encoding imposes, in the interest of meeting the real time, not having to be exposed to those latencies. That would sort of be the change of paradigm. It may or may not be reasonable, especially if parts of that transmission link are wireless and you have to eat a very large amount of bandwidth. So as a one additional illustration here, like an example of what type of things run here, let's see. Yeah, I'm sorry for this, so many. Essentially, the problem here is that this looks sort of impressive, but one has to be really careful when you look into, for instance, the tracking capabilities. You never want to lose a pedestrian. So when you evaluate this very rigorously in terms of, oh, what is the quality of my tracking, it requires quite a lot of work not to have interruptions in tracking, for example. Okay. And yes, we need high bandwidth wireless communications. We have to make sure that interfaces between wireless and fixed communications are very solid. We need very low latency, and we need very powerful computing resources, which in principle exist. But it is fair to say that right this moment, for instance, GPUs are not built having in mind very low latencies or predictable latencies. So that is probably going to change. For instance, they don't have watchdog timers such as the modem processors have. They can't really guarantee the time. So anyway, meeting the real-time expectations for applications such as the one that I've put in this set of slides is really not simple. You have a system-level challenge because you have to acquire the video. It's being compressed and transmitted. And because of the fact that the inference engines, the artificial intelligence, so deep learning inference engines also require lots of compute capability. In terms of the future, how the wireless is going to go, one of the possibilities is, oh, maybe sometimes I don't want to do encoding. Maybe I can do the raw transmission. If it's possible, I might be able to deal with some of the latencies differently, or in a... So this is where we are, and this would be the end of my presentation. Thank you.
Thank you very much, Zoran. I guess we have maybe a question or two. Anyway, we are through the allotted time, but here is one question, Zoran. Maybe you can.
Can you read it for me? I'm fishing for the question. So. Sure.
So, what kind of latency is added by the video compression? And you touched on that, but.
Okay, so this is the issue. There are two main components. What type? Do you include the temporal? The video encoding can have temporal component to it because you have different types of frames. So if you choose the least amount of compression, you may want to not to have temporal encoding. In theory, in which case the delay may be 33 milliseconds, exactly one frame. The second thing is that even if in theory that is possible, the way that the system is configured or the tools that configure it is non-trivial. So in practice, what you would see today, the systems that may give you one frame of latency, which is 33 milliseconds just on its own, may actually give you a 1 second delay. So where that leads us is that attempting to use the equipment that is non-controllable or that you can't manipulate and set up properly is not going to get us to meeting the real time. Okay, so we're considering adding, experimenting with raw data transmission from cameras without video encoding, just to see, and with very, very high bandwidth through the channel, just to see, can we have better latencies?